Today, I'll be presenting the first part of our group assignment focusing on the projection welding, specifically its definition and core technique. If we look at the slide, projection welding is formally defined as the variation of resistance welding where the electric current, heat flow are concentrated exactly at the point of contact with a local geometry extensions. To put this into the perspective, let's contrast it with a process many of us are familiar with, a spot welding. Unlike spot welding, which is heavily limited by the specific shape and size of the electrode tips, projections welding uses customized, pre-designed projections or small raised dimples embossed directly onto the workpieces itself. By using these geometry extensions, we can use the large flat electrodes. The projection acts as a localized point that focuses all the electrical resistance and heat generation right where we want the weld to happen. This clever design allows for a clean, efficient, and highly precise joints.
Today, I will explain the procedure of projection welding. The projection welding is a type of resistant welding that uses small raised point called projection to concentrate heat and produce strong weld joints. The first step is surface preparation. Before welding begins, the metal surface must be cleaned properly. Any dirt, rust, oil, grease or paint must be removed. This is important because dirty surfaces can increase unwanted resistance and reduce the quality of the weld. Clean surface help produce a stronger and more reliable weld joint. The second step is forming the projection. Small raised sections are created on one of the metal workpieces using a stamping or pressing process. This projection acts as concentrated contact points during welding. When current flows through these small areas, heat is focused at the projection, allowing the weld to form efficiently. Next is positioning the workpieces. The metal parts are placed between two copper alloy electrodes. The workpiece containing the projection is aligned carefully with the second workpiece. Proper alignment is very important because incorrect positioning may produce weak or uneven weld. After positioning, force is applied by the electrode. The electrode presses the metal parts together with a controlled amount of pressure. This pressure ensures a good electrical contact between the workpieces and help prevent sparking or arcing during the welding. The next step is passing the welding current. A high electric current flows through the projection for a short period of time. Because the projection area is very small, electrical resistance becomes high at that point. The heat generated can be represented by Q equal to I square RT. This heat causes the projection to melt and collapse, forming a weld nugget between the two metal parts. Holding and solidification. After the current stops, the electrode pressure is still maintained for a short time. This stage is called the holding stage. During this process, the molten metal cools and solidifies, creating a strong weld joint. The final step is cooling and inspection. The welded joint is allowed to cool before the inspection is carried out. The weld can be checked visually and tested, ensure it has a good strength and quality. That's all from me. Thank you.
Next, I will explain the advantages of projection welding. The first advantage is high production speed. Projection welding can perform multiple welds at the same time, which makes it very suitable for mass production industries such as automotive manufacturing. The second advantage is strong and uniform weld quality. Since the heat is concentrated at the projection points, the welds produced are consistent and reliable. Another advantage is less electrode wear. Compared to spot welding, the electrode in the projection welding lasts longer because the heat is focused mainly on the projection instead of directly on the electrode tips. In addition, projection welding provides a cleaner and smoother weld appearance with fewer surface marks on the metal. This method is also suitable for welding complex components such as nuts, bolts, and specially shaped metal parts. Lastly, projection welding reduces metal distortion because the heat is concentrated only at specific point. In conclusion, projection welding is efficient, reliable, and widely used in industries that requires fast and high-quality welding processes.
For the disadvantages of projection welding, one disadvantage is the high equipment cost because special welding machines and electrodes are required. It also requires precise projection design to ensure good weld quality. In addition, it is difficult to weld very thick metal materials effectively. Another disadvantage is electrode wear due to high heat and pressure during welding. Precise alignment is also necessary to avoid defective welds. Lastly, projection welding is not suitable for irregular or complex component shapes.
Atomic hydrogen arc welding. Atomic hydrogen arc welding, also known as AHAW, is a type of arc welding process that uses an electric arc between two tungsten electrodes in the presence of hydrogen gas. During the process, the electric arc breaks hydrogen molecules into atomic hydrogen. When the hydrogen atoms recombine into molecules, a very large amount of heat is released. This extremely high temperature is used to melt and join metal workpieces together. Hydrogen gas also acts as a protective shield that helps prevent oxidation and contamination during welding. Because of this, the welding process can produce clean and high-quality welds. Atomic hydrogen arc welding is commonly used for welding high-grade steel and metals that require precise welding quality. However, this method requires skilled operators and specialized equipment due to the very high temperatures involved. In conclusion, atomic hydrogen arc welding is an advanced welding technique that produces strong and clean welds joined using hydrogen gas and electric arc heat.
Next, I will explain the procedure of atomic hydrogen arc welding. First, the metal surface is cleaned to remove dirt, rust, and oxide layers. Then two tungsten electrodes are positioned with a small gap between them. Hydrogen gas is supplied between the electrodes and an electric arc is created. The arc heat dissociates hydrogen molecules into atomic hydrogen. When the hydrogen atom recombine near the workpiece, instant heat is released. This heat melts the base metal and field rods to form the weld joint. Finally, the molten metal cools and solidifies into a strong weld.
Today, I will explain the advantage of atomic hydrogen arc welding, also known as AHW. Atomic hydrogen arc welding is a welding process that uses an electric arc between two tungsten electrodes together with hydrogen gas to generate extremely high heat. This method is mainly used for welding high quality and alloy steel. One of the main advantages of atomic hydrogen arc welding is its ability to produce extremely high temperature. The temperature can reach around 4,000 to 6,000 degrees Celsius, which is much higher than many conventional welding methods. Because of this, the process is very effective for welding metals that require high heat input, such as stainless steel and alloy steel. Another important advantage is the excellent weld quality produced by this method. The hydrogen gas acts as protective shield around the welding area. This prevents oxygen and other contaminants from reacting with the molten metal. As a result, the weld become cleaner, smoother, and stronger with minimal oxidation. Another advantage is precise heat control. The welder can control the arc and heat more accurately, making this method suitable for precision welding and thin metal materials. It is especially useful in industry where high accuracy and strong weld joint are important. Furthermore, the tungsten electrodes used in this process are non-consumable. This means the electrodes do not melt easily during welding, allowing the arc to remain stable and consistent throughout the process. Lastly, this method produces very strong and durable weld joints. The high heat penetration helps ensure good fusion between the metal surfaces, resulting in reliable and long-lasting welds. As a conclusion, atomic hydrogen arc welding offers many advantages such as extremely high temperature, clean weld quality, no slack formation, precise heat control, stable arc performance, and strong weld joint. This advantage makes it suitable for high quality and precision welding application. Thank you.
Moving on to my second assigned topic, let's look at the other side of the spectrum, the disadvantage of the atomic hydrogen arc welding, starting with the major operational barrier. While atomic hydrogen arc welding is a powerful thermochemical process capable of producing massive heat, it introduces significant real-world challenges. First, high initial costs. So setting up an AHW system requires a high initial capital expenditure. This is due to the complex specialized equipment needed, including a unique dual electrode torch and precise hydrogen gas delivery and regulator system, making it far more expensive than standard MIG or IG welding setups. Limited positions, the process is severely restricted primarily to flat or horizontal welding positions. It becomes highly difficult for an operator to manipulate or control the weld pool for out-of-position welds, like vertical or overhead welding, due to inherent arc instability. Beyond operational barriers, we must also address the critical safety and material constraints shown on this slide. These factors dictate where and when AHW simply cannot be used. First, explosion hazard. First and foremost is safety. Because hydrogen gas is highly flammable and highly volatile, any system leak can easily lead to catastrophic accidents or explosions if a rigid, strict safety protocol is not flawlessly maintained. Second, skill intensive. So this method requires exceptionally high operator skill. The welder must manually maintain a precise arc length and delicately control the intense heat output, leaving a very small margin for error. Third, a burn-through risk. Because the extreme temperatures generated by the recombining hydrogen atoms can exceed 6,000 Celsius, AHW is completely unsuitable for lower melting point metal like aluminum or magnesium. Attempting to weld these thin or low temperature materials result in instant burn-through. So third is a hydrogen embrittlement. Finally, there is a severe metallurgical risk of cold cracking. So if atomic hydrogen gets trapped within the microstructure of the specific high strength steel, as the weld metal cools down, it compromises the structural integrity, causing the metal to become brittle and prone to fracturing. When we look at all this operational safety and metallurgical constraints together, it becomes clear why modern industries have largely shifted toward the safer and more cost-effective alternative. That concludes my part of the presentation. Thank you very much for your time.